Hello everybody. In this video we're going to be going over section 11.3, solubility. First thing we're going to do is describe the effects of temperature and pressure on solubility. We're going to state Henry's law and use it in calculations involving the solubility of a gas in a liquid. And we're going to explain the degrees of solubility possible for liquid-liquid solutions. First, let's define what solubility is. The solubility of a solute in a particular solvent is the maximum concentration that can be achieved. So it depends on the identity of the solute, and it depends on the identity of the solvent, and it's only true under given conditions. So we've seen that temperature and pressure can both affect the solubility of the solute. And what it is this is when the dissolution process that we've been talking about is at equilibrium, meaning that an equal amount of the solute is going to be moving into the solvent and dissolving, as will be coming out of the solvent and back into the solute phase. A solution whose concentration is equal to its solubility is what we call saturated. It has the maximum amount of solute possible given those conditions in the solvent. If the solution is if the solute is less concentrated than its solubility, the solution is unsaturated. You can still fit more solute into the solution. Solutions with relatively low solute concentrations are called dilute, and solutions with relatively high solute concentrations are called concentrated. It is possible to have what we call a supersaturated solution, right? And this is solutions with solute concentrations exceeding their solubility. So just like we can have unsaturated solutions where we're able to add more solute into the solution, we can have a condition where we have too much solute in solution. But this is still a non-equilibrium condition. So just like before, where we would have had more solute going into solution, when we have a supersaturated solution, we're going to have the solute coming out of solution, all right, until it reaches that saturation point. So this is not a stable condition, being supersaturated. Let's talk a little bit about the solutions of solutions of gases and liquids. So as we know, gases typically only have very weak intermolecular forces. Therefore, there is little to no solute-solute interaction to overcome during the solvation process. So when the solvent solute, okay, so the stickiness between our liquid and our solvent and our gas solute interactions are stronger than the solvent-solvent interactions, the stickiness of the different liquid particles for one another, interactions in solvation is going to occur. All right, so when the gases would rather stick to the liquid than the liquid would rather stick to itself, we're going to see solvation. The consequence of this is that gases are more soluble in solvents with weak IMFs, all right, so liquids that aren't very sticky with one another, and gases capable of forming stronger IMFs are more soluble. All right, so if the gases can form a stronger interaction with the liquid, they're also going to be more likely to dissolve. If we take a look at the effect of temperature on the solubility of gases, we're going to see that gases tend to be more soluble at colder temperatures. As the temperature of the solution increases, the solubility of the gases goes down. You may have noticed this in something like a pop, right, or a soda. If it gets hot, then it goes flat. That's because the CO2 that's making all the bubbles in there is becoming less and less soluble, and it's coming out of the solution. This same effect has major consequences when we start talking about climate change. As the temperature of the entire planet increases, the amount of dissolved oxygen and dissolved carbon dioxide in the air is getting to be, or in the water, is getting to be less and less. Um, Fish need oxygen that's dissolved in the water. So if they don't have enough oxygen dissolved in the water, they will die. And carbon dioxide, one of the major greenhouse gases that we're trying to sequester somewhere and not have go out into the atmosphere, is being released by our oceans, and that's really exacerbating the problem. Where that used to be a sink where we could add excess carbon dioxide, we're now seeing that it's just this warmer water is just helping to contribute to the release of carbon dioxide. So let's take a look at gas solubility and how it relates to partial pressure. The solubility of gases increases with the partial pressure of the gas above the liquid. And this is pretty intuitive, right? If I charge the top of the solution with a high pressure of a specific gas, it's going to go into the solution. That's how we make pops and stuff in the first place. We're charging the top with carbon dioxide and it's going down into the solution. When I release that pressure on the top, like when the pop fizzes and the carbon dioxide goes away, it's going to come out of the solution and decrease its solubility. There is a relationship, a mathematical relationship that we have here. So many gases under most conditions are going to follow what we call Henry's law, where the concentration of the gas that can be dissolved has a linear relationship with the partial pressure of the gas above the liquid. There is a constant right here, and this constant is going to be specific to the gas that we have above the liquid. It is not true that all gases are going to behave and follow Henry's law, and the reason that we see most deviation is because some gases are going to have reactions that occur between the solute and the solvent. For instance, this is ammonia, right? And ammonia is a gas under normal circumstances, but we do have that cleaner that we call ammonia. And what that is we've taken that gas and we've added it to water. So we dissolve the gas in water and we get this reaction here where we form these ions, which we would typically call ammonium hydroxide. So actually, the ammonia cleaner that you have is a solution of ammonia gas in water to form ammonium hydroxide. And then we've been talking a lot about POP so far, and that also has a reaction that occurs. When we add CO2 to water, we form carbonic acid. Carbonic acid will then dissociate out into ions. So POP is not one that's going to actually follow Henry's law. So let's talk for a minute about solutions of liquids and liquids. So what is true is that sometimes, and this is actually fairly rarely, solutes and solvents can be mixed in any proportions. All right, so I can have just as much solute as I want as I have solvent. They could be 50-50, and we could even have a situation where they switch, where the solute actually becomes the majority component and it takes over the role as a solvent, and the solvent becomes a solute. And this is what we call infinitely soluble. All right, so I can mix them in any proportions that I want. Liquid-liquid solutions that are infinitely soluble are called miscible with one another. All right, so no matter what proportions I mix them in, they're going to form a solution. Miscible liquids will have very similar properties, meaning that the two liquids will be similar to one another. All right. This means that the solute-solute, solvent-solvent, and solute-solvent IMFs will have comparable strength to one another. Polar solvents will dissolve polar solvents. So if we have dipole-dipole interactions, if we have hydrogen bonding, then we're going to be able to dissolve a liquid that has those similar properties, those dipole-dipole interactions or hydrogen bonding. And nonpolar solvents are going to dissolve nonpolar solvents. So if we only have dispersive interactions, we're typically only going to be able to dissolve dispersive liquids in that. This has a little phrase that goes along with it: like dissolves like. All right, so you're not necessarily going to be able to dissolve a nonpolar solute in a polar solvent, and you're not going to be able to dissolve a polar solute in a nonpolar solvent. So we've talked about when they're infinitely soluble, but when only a moderate portion of one liquid will dissolve in another liquid, they're called partially miscible. So you can have just a small portion that's able to dissolve, and when they completely will not mix, like in the case of having a polar solute in a nonpolar solvent or vice versa, they're called immiscible. All right, so they will not mix. And when you mix two immiscible liquids, they're going to form two layers with the less dense liquid on top. All right, you may have seen this with like salad dressing and vinegar or something. You let them settle, and they're going to form two layers. It is rarely, if ever, the case that two liquids have zero mutual solubility, though. All right, so even when we talk about them being immiscible, some very, very small negligible portion is still going to dissolve in the other phase. So let's talk a little bit about solids and liquids. The big takeaway here is going to be that typically the solubility of solids and liquids increases with temperature. All right. So when we have two condensed phase solids and liquids, we don't need to take into consideration the pressure, but only really the temperature. So leveraging the temperature dependence of solubility of solid liquid solutions is the most common way of preparing supersaturated solutions. So what I'm going to do is I'm going to heat up my solution. I'm going to put a whole bunch of sugar in there, and then I'm going to cool it back down. At some point, the concentration that was here is not going to be able to hold as much at a lower temperature, and I'm going to have that supersaturated solution. While it does tend to go up, you can see that some solids have pretty constant solubility, whereas some are going to be very temperature dependent. And that really has to do with the thermodynamics of the solvation reaction, and in particular, how much that enthalpy term is changing and how much of it is just being driven by the increase in entropy.